Welcome to Calculus 3. This is section 13.3 in your ApexCalculus textbook. This is on polar coordinates. So let's let x, y be a point in Cartesian coordinates. This is the normal rectangular coordinate system that we deal with. And so we want to look at the relationship between the xy coordinates that we're normally dealing with polar coordinates, which is in terms of r and theta. So let's suppose we have here the point x comma y. In polar coordinates, we have the radius r and the angle theta as the way that we could draw theta out here as a better way to represent it, as r comma theta as a representation for polar coordinates here. And so we need some connection between r and theta in a sense of triangular system with x and y. So we have the relationship, if we think about this in right triangle trigonometry, that x squared plus y squared is equal to r squared. This is your Pythagorean theorem that if x and y are the height and the base of the triangle, respectively, then r squared is the hypotenuse. We can also think of this as as x is equal to r cosine theta, and y is equal to r sine theta, and that the tangent of theta is equal to y over x, the opposite over the adjacent side. These four points are helpful identities for converting rectangular coordinates or Cartesian coordinates into polar coordinate systems. So one thing to note is that when we do a polar transform or transformation from polar coordinates and Cartesian coordinates, we have to account for the change in area, just as if we did in U substitution. And we'll talk about that with the Jacobian. And so with the Jacobian, what we have here is, let's refresh ourselves with U substitution. So let's first recall the idea of U substitution. So U substitution, if we had an integral, let's say, as 1 minus x squared quantity squared times x dx, we would make our substitution as u is equal to 1 minus x squared, du is equal to negative 2x dx, and that converts our integral as to negative 1/2 du is equal to x dx. So here we're scaling our change in u by an additional factor. This is the Jacobian. This negative 1/2 is a scale factor on our new variable u. So we're making a coordinate transform from the x system into the u system. And the Jacobian accounts for a scalar factor in order to preserve the same area that we're covering. And so if we were to continue this problem, we would see that we would have the integral of u squared times negative 1/2 du, which is easily solved as negative 1/6 u cubed, which is equal to negative 1/6 quantity 1 minus x squared cubed plus c. And that would be our answer for this problem. So we've seen Jacobians before, we just never called them that when we did U substitution. So again, the Jacobian scalar is really what we're doing when we're moving from one coordinate system in the case of x into another coordinate system in the case of u. So we just have to do the same thing when we're converting from Cartesian coordinate systems to polar coordinate systems. So because we're dealing with two variable systems, we have to make sure that we calculate the Jacobian accordingly. So the Jacobian for polar coordinate systems is easy to calculate. And in fact, it's easy to calculate for many systems, but let's do it simply for polar coordinate systems. So if you've taken linear algebra, you might be familiar with determinants. But the Jacobian for polar coordinate systems will recall that the determinant of a matrix A, B, C, D is equal to the multiplication of the diagonal AD minus the off diagonal BC. So for any matrix A, B, C, D as indicated, you take the elements on the diagonal minus the elements on the off diagonal. So for polar systems, we're looking at the determinant of the partial derivative of one variable with respect to the partial derivative of the other variable. And so we look at a particular pattern of partial derivatives. So partial r, partial x over partial r, partial x over partial theta, partial y over partial r, partial y over partial theta. We're looking at the determinant of this matrix. So this, what we have is we have partial x, partial r, times partial y, partial theta, minus partial x, partial theta, times partial y, partial r. Recalling for our formulas that x is equal to r cosine theta, and y is equal to r sine theta. So if we're looking at our determinant here, partial x with respect to r is cosine theta. Partial y with respect to theta is r cosine theta. So we have, again, y as a function of theta. So r is a constant when we're looking at the derivative with respect to theta. And then the derivative of x with respect to theta is r negative sine of theta. And the derivative of y with respect to r is sine of theta. And so we get r cosine squared of theta plus r sine squared of theta. And using our Pythagorean identity, we see that this just gives r. And to be very precise, each of these pieces, x with respect to r, we can think of this as a chain rule. So we tack on a dr d theta at the end of this. So for each of these pieces, when we're doing our derivative with respect to r, we have cosine of theta dr. You can think of there's a little dr and there's a little d theta in here. R sine of theta, there's a little d theta, and there's a little dr in here. So we can think of these infinitesimally small dr and d thetas floating around in our problem, but convention is you just tack them on at the end of the problem. So the Jacobian, the key point is the Jacobian for polar transformations is that anytime you do a polar transformation, you will add on the r dr d theta when you do the transformation. And that's the key point of this. But if you forget the key point, you can always rederive the polar transformation. And this works out whenever you have any coordinate transformation. You always look at the change in one variable with respect to the other, so the matrix of partials, and you can calculate the determinant of that. And this works for any number of change in variables. So if you have 3 variable system going to a 3 variable system, you can calculate the determinant of that matrix, and you will get the Jacobian for that. So let's look at an example here of how polar coordinates are helpful. So if we consider a region R where we have the function x is defined from -2 to 2, and y is defined, x here, and y is defined on the interval 0 to square root of 4 minus x squared. To visualize this region, we know that y is the y-axis as one of its bounds. So let's go ahead and indicate that in red. So that's our lower bound for our y region. X is bounded from -2 to 2. And our upper bound is this upper half of the circle of radius 2. So it looks like we have the upper hemisphere of a circle. So this is our region R. And let's suppose that our function that we're looking for, f of x, y, if we're just looking for the area of this region, So let's just suppose that that surface has a height of 1. So if we're setting up our integral, we can set this up just the same way as we did in the previous sections, 0 to square root of 4 minus x squared of 1 dy dx. So far, this is nice and easy to solve. Negative 2 to 2 of square root of 4 minus x squared dx. Now, when you look at this, there's no u substitution that will make this work. This is not a nice, easy problem to solve. This is, in fact, something that you could use a trig substitution problem for. But if you recall from your Calculus 2 class, trig substitutions may not be your best friend. So let's look to see how to solve this in terms of a polar transformation. So we know that this is a circle of radius 2. This is the upper hemisphere of a circle of radius 2. So if we know things about a circle of radius 2, so our radius has to go from 0 to 2. If we think about, let's draw this diagram again. We're drawing our diagram and we have this circle from radius 0 to 2. Our rectangles now are radius lines. So we start at the radius equals 0 and we go out to r equals 2. So we think about starting at the origin and emanating a ray out to the value where r equals 2. And then our theta goes up from 0 and it sweeps around the circle until we get to pi. So now as we're sweeping through our integral, this looks like theta goes from 0 to pi and r goes from 0 to 2. Our inner function is still constant, so it still stays the same. And we tap on the Jacobian r dr d theta. Notice that we're keeping our bounds in order, and this is our Jacobian. So this integral is much easier to solve. So we have 0 to pi of r squared over 2 evaluated from 0 to 2 d theta, which looks like 0 to pi of 2 d theta, which gives us 2 pi. So conceptually this makes sense because if we check it with geometry, we have the idea that the area of a circle with radius 4 is we have pi times our radius squared, so we would get 4 pi for the full circle. So we would get 2 pi for the half circle. So this makes sense with our intuition. So the next video in this section, we'll go through several examples where we will talk about how to use polar coordinates with integration.